let me say a few more words about Lagrange's theorem and cosets in general. So recall Lagrange's theorem. It says that if G is a finite group and H is a subgroup, then the order of H divides the order of G. Let's look at this particular situation here. If I take G to be a group, it doesn't have to be finite at the moment, and I look at a following subset of G, namely I pick one element, little g and big G, and I look at all its powers, all possible integer powers of G. So first of all, I claim this is a subgroup of G. Clearly it's a subset closed under the group operation, because if I take G to the n and multiply it by G to the m, then I get G to the n plus m, so also a power of G. Secondly, the identity is there because the identity is G to the 0, and the inverses are there too because the inverse to G to the n is G to the minus n. So it's a subgroup of G, and secondly it's a cyclic subgroup because by definition the subgroup is generated by the element little g. So in every group, one way to create subgroups is to take any element in that group and look at all its powers. So this leads me to one consequence of Lagrange's theorem. So proposition 1, let G be a finite group. And little g be an element of G, then the order of G divides the order of big group. How do we prove it? Well, it's actually very easy. So consider the subgroup. This subgroup, the one I was just talking about, which I'm going to now write like this, the cyclic subgroup generated by G. So in other words, that's the G and N and Z. In G. As G is finite, this subgroup also must be finite. G is also a finite. Maybe let me just say it's a finite cyclic subgroup. So we know that for finite cyclic subgroups, the order of the generator is equal to the order of the group. So it is, okay, it's the order of the group generated by G, right? That's a group, and that's the order of the group generated by G. But on the other hand, this is a subgroup of, so as G is a subgroup, of big G, we get by Lagrange Lagrange's theorem that the order of the subgroup divides the order of the group. So we are done, because the order of the subgroup is equal to the order of the element G. We get also that the order of the element G divides the order of the group. Okay, so that's one property of, one consequence of Lagrange's theorem, that if I have a group of order 50, then the orders of the elements can only be the divisors of 50. This has a very important consequence. So corollary, let's call it corollary 2. Every group of order P, all right, let P be a prime. Every group of order P is isomorphic to Z mod PZ. So in a sense, you can say up to isomorphism, how many groups of order 17 are there? In fact, they're all isomorphic to Z mod 17Z. So if you just look at through the telescope of group theory, you do not see many groups of order 17, namely only one up to isomorphism, so Z mod 17Z. How do you prove this? So proof, let G be a group of order P, which is prime. Well, then G is not the trivial group. So there exists an element, G in G, such that the order of G is not 1. The only element in a group of order 1 is the identity. But because G has prime order, the smallest prime is 2, there's definitely an element in that group which isn't the identity. However, by proposition 1, we get that the order of G must divide P, because the order of any element must divide the order of the group. But P is prime, so what are the positive integers that divide P? Only 1 and P. So the order of G must be equal to P. But if I have a group whose element has order P, that means that the group is cyclic. So let's just write it this way. E, G, G squared, all the way to G to the P minus 1 are all distinct elements of G. And how many do I have here? I have P, so that means that exhausts already all the elements of G. Right? I have P of them here. P elements. So that means these are all the elements of G. Are all distinct elements of G. So every element of G is a power of G. Hence, G is cyclic. Generated by G. As we already know, as any cyclic group of any given order, so in this case of order P, is isomorphic to Z mod PZ, we are done. So every group of order P is isomorphic to Z mod PZ, and in fact every non-identity element in that group is a generator, because every non-identity element will have to have order P. Let's just do maybe one little example of this. If I look at the group D10, then inside it, I have the group generated by, I can look at the subgroup generated by rotations, so consisting of rotations. Right, so these are, so R is a rotation counterclockwise. By 72 degrees. This is a subgroup, and what do I know about the subgroup? It's cyclic, generated by R. It has 5 elements. It's isomorphic to Z mod 5Z. See, even if I didn't know it was cyclic, generated by R, even if I just wrote this is rotation by 72 degrees, rotation by 144, rotation by whatever 144 plus 72 is, and I somehow didn't notice that you can get rotation by 144 degrees by combining two rotations by 72, so I would just have these different 5 rotations here, and I know they form a subgroup. Just from the fact that the order of the subgroup is 5, I would have known that the subgroup is generated by the subgroup is isomorphic to Z mod 5Z. So in particular, it's cyclic. Okay. Proposition 2. So again, let G be a finite group. And H a subgroup of G. Then the index of H and G is the order of G divided by the order of H. The index, remember, by definition, this is the number of left cosets of H and G. Why is that true? Well, that follows not exactly from Lagrange's theorem, that follows from the proof of Lagrange's theorem. If you just look at the last few lines of the proof of Lagrange's theorem, you see that the way we got this divisibility was we wrote the order of G as the order of H times the number of cosets. So in other words, times the number of left cosets. So in other words, the number of left cosets is equal to the ratio here. So I'm just going to say proof. It follows not so much from Lagrange's theorem, but it follows from the proof, from our proof of Lagrange's theorem. And the last thing that I wanted to do here is to look at this index, and I would like to say, well, there's some asymmetry here in its definition. It's the number of left cosets of H and G. What about the number of right cosets of H and G? Do I need a separate sort of right index here? It turns out the answer is no. The number of left cosets is always equal to the number of right cosets, but that requires a proof. So let's state it as a proposition. So this should have been proposition 3 really here, because we had corollary 2, proposition 3. So now proposition 4. Let G be a group, not necessarily finite. I don't need finiteness for this. Let H be a subgroup of G. Let SL be the set of distinct left cosets of H and G. So in particular, if H is a finite index, that's just finitely many here. So distinct cosets, right? If two cosets, any two cosets are either equal or disjoint. So I'm just putting the disjoint ones. So if I have GH and G prime H and they are the same coset, I'm only going to put one of them, say GH. I'm not going to put G prime H. So in other words, these are distinct left cosets of H and G, and let SR be the set of distinct right cosets of H and G. Then there exists a bijection SL to SR. In particular, if SL is a finite set, then so is SR, and they have the same number of elements. If they're not finite sets, this just shows that they have the same cardinality. In any case, there's a bijection, so I want to construct that bijection. All right, so how am I going to do that? Before I do that, I wanted to remind you some properties of cosets, which is sort of going to be our sort of black box here. Some of them we proved before, some of them I asked you to prove. So if I have A and B in G, then we have the following. Actually let's do A, B, C, and D in G. AH is equal to BH if and only if A inverse B is in H, if and only if B inverse A is in H. On the other hand, so this we proved, but there's property also for right cosets which we didn't prove, but you can prove it the same way we proved these properties for left cosets. So HC is equal to HD if and only if DC inverse is in H, and if and only if CD inverse is in H. You see, they're different, right? The inverses in the first case show up on the left, and here the inverses show up on the right. Okay, so we're going to use those things in our proof. So how does the proof go? I'm going to construct this bijection. So first I'll construct a map. So let SL be like this. Let's just say H, sorry, these are left cosets. So GI sub H, where I is in I. So these are distinct cosets, right? So GI H is equal to GJH if and only if I is equal to J. All right, so I'm looking at some, I took some cosets here. These are distinct cosets, and these are all the cosets. And I is just some indexing set here. If there are finitely many cosets, this just goes, I can just be numbers 1 through n. But if it's infinite, then it's just some indexing set. Okay, and I'm going to construct a map. I'm going to set phi from SL to SR to be phi of a left coset to be equal this right coset. Okay, so we need to show that this is a bijection. Right, so any left coset here, distinct left cosets are mapped to right cosets. Note that I don't have to check well-definedness because these are distinct left cosets, so there are not two ways to write the same coset. And they give me some right coset. Okay, so I need to prove that it's injective and surjective. So injectivity of phi. So suppose phi of GIH is equal to phi of GJH. Right? What do I want to prove? Want to show that GIH is equal to GJH, i.e. that I is equal to J. All right, so let's do that. What is this? So the left-hand side, this thing is by definition HGI inverse, and this thing is HGJ inverse. Okay, these are right cosets. So I'm thinking of this here as C, and of this here as D. Look at this. HC is equal to HD. And so I'm going to use this property, HC is equal to HD, if and only if. So I get D, so GJ inverse, C, maybe let me just use the blue color, this was better. So D, so GJ inverse, C, so GI inverse, sorry, it should be DC inverse. This is C inverse, must be in H. Right? The GJ inverse, that's D. And the GI, that is C inverse. DC inverse should be in H. All right. But now I'm going to treat these as I'm going to write this as B inverse, and this thing is A. And I'm going to read from there what that means for left cosets. So if this is B inverse and this is A, then I get, okay, so I have B inverse A. B inverse A is in H, so that means AH, so GIH is equal to BH. So this is B inverse, so GJH. Right? Again, this is then A, and this is B. Right? If this was A and this was B inverse, then this is A and this is B. So, look, I've showed exactly what I want. So I get injectivity. So now, surjectivity. So I want to show that I get every coset inside SR.